Most people learning robotics waste their years behind the YouTube tutorials and they end up with no actual industry level projects. The difference between a robotics engineer and a hobbyist is clearly not about complexity of the work. It's totally about knowing which systems does a real world robotics company uses while shipping their product. This is your roadmap to bridge that gap. What does industry grade robotics mean in 2026? This roadmap will provide you a detailed guidelines which you have to follow to be a robotics engineer who can create a industry level projects in 2026. Most learners get stuck into this loop. They start with a YouTube tutorial, they pick a random projects that they can work on it, and then they end up with no system level thinking and no industry role is played by that particular project. So what is the difference between a hobbyist and a real industry engineer? A hobbyist approach is they start with a Arduino based projects, they write a single script solution and they work based on the trial and error methods, and then they focus on the individual components like sensors and cameras, how to integrate it. They build their project and they end up with nothing. This is not a real robotics engineering code. So let's be practical. When a robotics company hire you, they don't ask you to build a robotics project using Arduino and Raspberry Pi. They need engineers who can build modular and software systems that control physical hardware safely and reliably. Industry grade means five specific things. First thing, you can architect ROS based software systems where sensors, actuators, and the logical components work properly through a well-defined nodes and topics. Second, you can understand the full stack of robotics from firmware running on microcontroller to the high-level motion planning algorithms. Third thing, you can simulate robots' behavior on tools like Gazebo before touching physical hardware because the real testing costs heavy. Fourth, you integrate perception systems like computer vision, sensors, slams that helps robots to understand the environment in which it is working. Fifth, you ship production code. It means that writing C++ code for real-time performance and handling edge cases with critical logics. So let me break the actual path from zero to industry grade. Phase 1, foundational layer for 4 months. You need two languages from day 1, C++ and Python. C++ is non-negotiable. It is a standard for low latency robotics. Companies usually use to write their codes in C++ so that the latency between the components are very less. What you need to understand? You need to understand pointers, memory management techniques, and object-oriented designs so that you can write a proper confident code. Next is Python. Python handles high-level controls, perception scripting, AI integration, and rapid prototyping. Academic labs and startups use this extensively for their research. Next is electronics and hardware basics. You need to understand how microcontrollers like Arduino and ESP32 works. These runs the firmware directly that controls motors, reads sensors, and handles real-time input-output. Maths that actually matters. Linear algebra for coordinate frames and transformation, calculus for control systems, and basic probability for sensor fusion and localization. Next is phase 2, core robotics stack for next 4 months. ROS2 is not optional. This is the software layer used by companies. Master nodes, topics, TF2, lifecycle nodes, and RCL-CPP in C++. ROS2 exists because industry needs real-time performance, security, and reliability. Start small, publish sensor data, subscribe to topics, visualize in Revizto. Then scale the multi-node systems where perception, planning, and control talk clearly. Next is simulation. Break codes, but not hardware. Gazebo and Ignition let you test robots in a virtual world. Simulation saves money and time. This is how actually companies build fast. Learn URDF to define robot structure and simulate sensors and actuators. Connect simulation with ROS so the same code runs in a sim and a real robot. Next is motion planning in a real robotic arm. If you are working with manipulators, you need Move It. Move It handles inverse kinematics, collision avoidance, and trajectory planning. You define robotic kinematics, plan safe motions, and execute them precisely. This is production grade robotics, not DIY control. Third thing is learning perception and autonomy for next upcoming 4 months. Computer vision, how robots see. OpenCV is the foundation for the robot vision. Use it for image processing, edge detection, motion tracking, and feature extraction. Pair it with YOLO V5 and Detectron 2 for real-time object detection and segmentation. This is how robots understand what's in front of them, not just see the pixels. Next is AI on edge hardware, from model to machine. Training a model is easy. Running it fast on a robot is the actual real challenge. Deploy models using TensorRT and Onyx runtime for low latency interference. Jitson Nano and Xavier are industry standards for embedded AI. This is how startups and AAV team runs 30 plus FPS vision on devices. Next is SLAM and navigation. SLAM lets robot map unknown environment and localize themselves. This is crew learning. Use cartographer, G mapping, or ORB SLAM 3 for mapping and loop closure. ROS2 Nav2 handles path planning, obstacle avoidance, and recovery. Without SLAM, there is no autonomous robots. Next is drone autonomy. Aerial robotics stack. For drones, learn PX4 and Arduino Pilot used in defense and industrial UAVs. Drone autonomy is specialized, but the core autonomy skills transfers everywhere. Next is embedded and real-time system, phase 4 for next 4 months. Firmware, where robots become real. This is where you control motors, sensors, and safety systems directly. Work with FreeRTOS or Z5 for real-time control. This code runs the robot at the lowest level. Mistakes here break hardware. Next, another thing which I must be discussing is why Rust is rising. C++ is powerful, but the thing is, it is risky in safety critical systems. Rust prevents more memory bugs by design, making systems safer. Used in drones, aerospace, and real-time control stacks. Learn Rust plus C++ for firmware. This combo will make you rare and valuable. As soon as you complete this, we will step into phase 5, product level engineering in 4 months. So how can you learn it? First is real robots are systems, not algorithms. Perception feeds, planning drives, control runs hardware. Design fault tolerant architecture that doesn't crash on its cases. Use lifecycle nodes, watchdogs, and clean module interfaces. This is where prototype becomes product. Want to be noted. Next is testing and validation. This is non-negotiable. Production robotics demand rigorous testing, unit tests, integration tests, full system tests. Build regression pipelines, log everything, analyze failures. If it's not tested, it's not shippable. Next is deployment and optimization. To the shipping codes. The robots run on limited compute at real-time speeds. Profile performance, optimize bottlenecks, reduce latency. Deploy ROS systems with Docker. Manage configs, monitor robots remotely. This is how leads stay alive in the field. So let's discuss about tools which we use in the companies. First one is ROS2 with C++ and Python. Move It for manipulation, Nav2 for navigation, and TF2 for transforms. Next is simulation. Gazebo for physics and sensors. NVIDIA Isaac Sim for high fidelity vision and synthetic data. It is also used for simulation to real pipelines. Next is perception. OpenCV for vision, YOLO V5 and Detectron 2 for detection. TensorRT for JSON interference, and Cartographer and OpsLam 3 for mapping. So next section is embedded and edge, STM32 and 10C for microcontrollers, free RTOS and Cypher 2 you can use, and JSON Nano and Xavier for AI robots, where high-level AI models are deployed. These come into the picture. Next is tools for drones. PX4 and ArduPilot, MavLink plus QGround control, and that's it. Next is supporting tech. MATLAB and simulation for control design. Node.js plus React for robot, dashboard and fleet systems. This is what companies use in warehouse automations, EV, surgical robots, and defense. Finally, we have reached to the end of the session today. What to do next? If you are a beginner, learn C++, electronics, sensors, and actuators. Suppose if you can code, jump into ROS2 and Gazebo. Or if you already use ROS, specialize deeply. For everyone, there is just one path: simulation first and hardware later. Use Jetson Nano, Turtlebot, drone dev boards. That's it. The robotics industry is growing very fast. Start today, build something, ship it, iterate. That's it. Smash that subscribe button before you start the journey.